Hello everyone, welcome back. Today the last class and I want to basically introduce you to some of the research topics which are done in the computational gas dynamics. So, till now we have understood the fundamentals, we know how to basically write a code to solve these problems or maybe use the commercial or open source codes to solve these problems, right. What I want to do today is that I want to take you through some of these research problems, okay, which are currently active. Okay, these are active research problems. These are not something which were done 20 years back. Okay, so that you will get a flavor of what kind of complex problems it can solve with the understanding that you have as of now. Okay, so the topic is shock wave bond-layer interaction. Okay, so till now what you have seen is if the equations are Euler, there is no viscosity, the shock wave will come and depending on that I mean it will. So, let me just show you an example. Okay, so this is for example, if the flow is Euler, okay, and let us say you have this compression corner. Okay, so you know that depending on what phi you have, okay, you may have a the oblique shock or a detached shock, right. You know this theta beta m relation. So, if you have an incoming boundary layer is there, okay, and if you are just saying that there is no I mean you are not introducing any you are not solving using Navier-Stokes equations, but only Euler equation, this is the structure that you are going to get. There will be shock there and the flow will accordingly change, right. Once you introduce the viscosity or the when you start solving the Navier-Stokes equations, the flow features becomes very complicated. Okay. So, because of the viscous nature, so the information is not traveling only in a certain direction as it happens in the case of supersonic flow or hypersonic flow, but it can travel everywhere. So, if you have so let us say in this example the flow is supersonic, so you are saying that it does not care about what is happening in the upstream direction. Sorry, in the I mean it will only look at what is going downstream like this, correct. So, in the boundary layer, however, what will happen when you introduce a viscosity, the flow goes to very small value, okay, and there is a viscous sublayer, okay, or basically let me call it a region where the viscosity is dominant. Okay. So, in that region the information can basically go upstream, okay, and because of that. So, you can see that because the information can go upstream and by default. So, when there is a shock the pressure increases. So, it is an adverse pressure gradient flow. So, here pressure is basically higher than the pressure that we have, right. So, normally the flow happens from high to low pressure, but because of the shock you are creating a situation where there is an adverse pressure gradient, right. So, this has to negotiate with the boundary layer, okay, and what happens because of that is that a separation gets developed because of this shock and boundary layer interaction. So, there is a shock here, there is a boundary layer, the field is viscous, okay, and it says that okay, at least near the wall, near the viscous region, okay, it is not obeying the hyperbolic law, it is kind of obeying the elliptic law where the information can travel every side and every place. So, then what will happen is you will basically see a separation region being formed, and because of this separation region you may have basically increase in the heat transfer rate, okay, and it is a phenomena which is still of research, and we are trying to understand how are the causality of this picture that we are talking about, whether the shock causes the separation or the separation causes the shock or how they interact, because this is highly unsteady also. You can see that there will be low frequency which is basically acting on this. So, it is moving, right. So, and then once it comes back, so there will be a separation shock also, okay, because of separation. Now, if you look at this region, now instead of seeing like this, the incoming flow is seeing a body like this, okay, because of the separation region. Okay. So, this is what we will have is the separation shock, okay, and this will form even if the body is like this, okay, and let us say there is a shock here and then you have a separation region coming like this, okay, this is a shock induced separation, and then you will have basically a reattachment shock, just like you have in the shear, there is a reattachment shock. So, it will try to reattach and there will be a reattachment shock, and then you will have slip line and some other things. Okay. So, the flow phenomena becomes very complicated, okay, and this is very common, let us say in the scramjet intake or the re-entry vehicle, supersonic aircraft. So, everywhere you have very close to the body you have the boundary layer, okay, and the shock. So, for example, if you look at here, these are the shock structures and they will interact with the boundary layer here, the boundary layer here, and it creates a very complex phenomena and it is highly unsteady. So, you cannot use, for example, a simple Raynes based solver, because the flow phenomena is highly unsteady and you want to capture the unsteadiness, right. So, at least you have to use the unsteady Raynes, right. So, you will have basically shock induced separation or the flow unsteadiness, instabilities, heavy thermal loads. It will also increase the turbulence intensity. So, this is all happening because of the shock wave boundary layer interaction. Now, this can be the boundary layer can be laminar or turbulent. So, if it is shock wave turbulent boundary layer interaction, then it is called SWTBLI, okay, or just STBLI. Okay, this is even more complicated because now you have turbulence also added to the complexity that we have, right. So, using even using a turbulence model to solve these kind of problems are complicated, because these are high speed flows. The models are normal turbulence models are designed for let us say low or moderate speeds, right. So, and then you have the interaction between the shocks and the boundary layers. So, it is not an easy problem for any computational model or any CFD code, right. So, so yeah, this is the example that I was talking about. So, let us say you have a basically shock generator, or from somewhere a shock is coming. So, this is an incoming shock. Okay. So, if there is a no viscosity, what will happen? It will come and get reflected like this, but because of the viscosity you will have basically this region where the it will get separated, and even if the incoming boundary layer is laminar, okay, because of this separation it will become like transitional or it can become turbulent, right. And because of this surface you will have basically an expansion fan which will come here, and then you will also have the reattachment shock or the reflected shock that we have. Okay. You can also have some more shocks, like there are the first reflected shock, okay, second reflected shock, which is this one. Okay. Yeah. So, to solve it, I mean just to give you an example. So, this is the example that I was talking earlier. So, this is a laminar, let us say laminar shock boundary interaction. So, you want to see flow over a wedge. So, this is a wedge at 15 degree and it will create a let us say an oblique shock. So, you can simulate it in open form, okay, and let us say this is the grid that you can make, okay, and finally, you can see that this is how the shock will develop, but I want your attention in this region. Okay. So, here it is not very clear, and you can see that this is basically going upstream, right. So, this is happening because we have chosen the laminar solver. If you take mu equal to 0, then you will get a clear solution which will basically be just a shock. Okay. But in this region you have this shock boundary layer interaction. Yeah. So, this is one example. Yeah, this is the 2D SBLI example where I want to impinge a shock. So, there is a shock generator and shock is impinging, and because this separation is forming, just what we discussed. Okay. So, how do you set it up? So, let us say this is my plate, okay, and then there is a shock generator, okay, which is creating a shock at a certain angle. Okay. So, you can say I mean whatever the angle that you have, okay, let us say beta, okay, and then it is getting reflected, and so you will give this pre shock condition here, okay, and the post shock on the all the domain in the right hand side. This is all the post shock condition in the beginning. This is at t equal to 0. Right. That means, you are saying that there is a shock which is impinging on the plate and you want to see what happens because of that impingement. Particularly, you are interested in the shock boundary layer interaction. So, what is happening, how it is interacting with the boundary layer here, is there a separation which is forming, right. So, this I have done using my own code. So, this is a kind of an LES problem. So, Reynolds number is 3 million, Mach is 2, and this is a valid oblique shock theta equal to 6 degree. right. So, once you solve it, okay. So, this is the initial condition that I was talking about, okay. This is the pre-shock, okay, and this is the post-shock, okay. This is at t equal to 0, and as time progresses you will see that this kind of structure will develop, okay. There is a, you will see a separation region, and this requires a very good solver, okay, and very nice grid. So, you can see this is a separation region, okay, and this is the reattachment shock. This is another shock that we talked about. This is the inlet shock, because we have not used any region before this, which is typically used if you want to, I mean typically slip line or slip region is used here, and the domain is extended here, so that you do not see this inlet shock, or you want to avoid this inlet shock. Okay, so, that solution first get developed here and does not see it abruptly, this point. If you right now I am just putting m equal to 2, it is like a plug flow. Okay. So, at m equal to 2 you see this discontinuity, and because of that this inlet shock gets developed. And this is how, for example, the pressure will look like, okay. And you can see that the pressure increases at shocks. So, wherever there is shock there is increase in pressure, okay. Here you can see an increase in pressure, okay. And because of this expansion there is a decrease in pressure, okay. And you can actually plot it, let us say along the wall, okay. Let us say you want to plot it along the wall, and I have compared it with the literature. Literature is provided in the, the literature is provided here, okay. The reference is given, and I mean you can basically plot it and see the accuracy of the solver. As I mentioned, it is not a simple problem, although it looks very simple, but your scheme should be very good, your grid should be very good. You have to use unsteady solver, okay, and then take a mean to basically see these kind of results. Okay. You can see that the shock rising here, and sorry, the pressure rising here and pressure rising here. If you look at the bottom, okay, that is because of the shocks. Okay, this is a movie. Unfortunately, it does not play here. Yeah, so next is the compression expansion corner. So, I am just giving you some problems which are of interest, is maybe of interest to you if you want to get into research. Okay. So, this is compression corner, and then you have an expansion. Okay. So, as you know from your gas dynamics theory that there will be shock which will form here, and then there will be expansion waves at the expansion corner. Okay. So, so these are basically the properties of the compression and expansion corner. The aim is to study the effect of successive distortion of the boundary layer of the flow. So, there will be distortion here and distortion here, okay, because of the shock and the expansion, and you want to see how it happens, and these are some of the parameters. Okay. So, Mach is 2.85, and this is taken from some experimental data. Okay, I am not sure if I have the reference. Yeah, so I have the references. So, basically Douglas and so Smith and Smits and Settles, they have done experiments on the similar configuration, and these are the bonding conditions that they have given. So, if you want to make solve this problem, so will basically you have to mimic the experimental setup that you have. So, this is the domain, okay, and then you apply this the boundary layer. So, there was a boundary layer, incoming boundary layer. So, you do not want to simulate the entire domain. So, you will apply a boundary layer here. So, that you can simulate separately, and this is the boundary layer that you see here, which is applied here at a given distance minus 2 delta naught, and that it is allowed to basically grow, okay, here. So, the initial boundary layer thickness is 23 mm, which is basically provided from the literature, and the intensity is 0.5%. This is a turbulent problem, and mu T by mu is chosen as 10. Okay. The is an isothermal wall. So, this is a heated wall, T W is more than T naught. Okay. So, it has been solved using two different solvers, row central form and sonic form, and they have certain differences. So, as I mentioned, this is the density based solver and this is the pressure based solver. Okay. This is completely explicit, it allows very small CFL number, in fact, less than 0.3 also sometime, but sonic form allows for a bigger CFL number. Okay. You use this Mentor's SST K omega ideal gas, okay, and Sutherland's for calculating viscosity. Yeah, so this I have not emphasized earlier. So, basically the viscosity also changes with temperature, and you have in the compressor flow you need to basically ensure that your viscosity is changing with the temperature, and this usually goes as nu is square root of T, or mu is square root of T. Okay, so you need to basically make sure that you are taking care of that. So there are I mean, these are very common laws available in the literature. So this is how the flow will develop. Okay, so you will have basically the sock here. In fact, this makes the things better and things clear. So this is, there is a sock here and there is an expansion fan here, and you can see that there is a separation region which is being formed because of the sock module interaction. Okay, if you do an Euler simulation, you will not see. Okay. Yeah, the next is the scramjet inlet. So, if you want to, let us say, simulate this scramjet inlet. So, here also this is my ramp side, on the top is the ramp side, okay, and the bottom is the cowl side, okay, and because of the successive compression due to the ramps, as you know that in the scramjet there are no moving parts. So, all the compression that you need for the gas to become combustible is done through the successive oblique shocks. Okay. If it is ramjet, then you may have normal shock also, right. So, the flow is still supersonic when it is being burnt, but the speed is lowered because of these successive shocks. So, we want to study is that can we resolve the shock structure here, okay. And secondly, how does this the shock or the flow which is coming from this side basically interacts with the modular, right. So, as you may guess that, okay, there may be separation here. Okay, there is an expansion fan, there is a separation, and because this shock is impinging on this. So, this leads to separation, but very close to that you have this expansion, and there is another expansion on this also. So, it is a very complicated phenomenon of shock interaction, shock expansion fan interaction, shock modular interaction, and it is a challenging problem for any CFD solver. Okay. And then you have so many shocks, okay, which are basically present inside the body. So, if you want to solve this again, I think we have taken some reference. Okay, I have not given the experimental reference, but yeah, you can find it from our paper in IGCFD by Kavan and Ranjan 2023. Okay, so here you can see that we have basically taken the domain as per the experimental data. Okay. I think if I am not wrong, it is by Reynolds, okay, and the Mach number after the first compression, the external compression is 2.41, Reynolds number per million per meter is 5.07 into 10^7, and these are the conditions for pressure, temperature and intensity. Okay, you have to of course make a grid accordingly, okay, and apply these boundary conditions. Okay, these non-reflection boundary conditions used on the right hand side, ramp and cowl. Okay, and this is the zoom region where you are expecting a separation to develop here. Okay, so, so as I mentioned that it is not an easy problem. So, this is solved using Fluent, and this is Fluent. Okay, so, if you use the default SST K omega model with a parameter which is called A1, okay, this is the structure parameter. It basically dictates that how much turbulence should be generated because of the shock, okay, and it actually generates a lot of turbulence, and that is why the separation size actually becomes smaller compared to what we have in the experiment. Okay, and because of that, the location of these the shocks at different places, you can see that it is not matching. Here it is impinging here, but here it is impinging here. So, we reduce the value of this A1. So, this is what I have been telling, that you may have to tune the turbulence model, okay, to get the results properly. Okay, and you can see that the separation size, this is the turbulence kinetic energy flow field, and the separation size basically increase as we basically decrease the value of A1. That means, we allowed less turbulence to create. So, that is why the separation size got increased here, okay, and then you can see it matches the result. Okay, this point and this point, the shock location and all these things. Okay, so, yeah, these are some of the things which there are ongoing research going on. Okay. Yeah, then you have, let us say you want to we are interested in unstart dynamics. So, if you look at the picture that we have earlier here, right. So, because of the burning of the fuel, the pressure increases, okay, and basically you have a push towards the inlet, and it leads to something called unstart. Okay, and when there is unstart, the flow will have difficulty getting in. Okay, and that is a dangerous thing, because it may stall the operation, right. So, we want to avoid the unstart. Okay. In order to do that, we have to basically understand what is the, how do you basically understand the unstart dynamics. Okay, so in order to basically mimic the combustion or the pressure rise at the due to combustion. So, what we have used is basically you have used the throttle. So, the domain is like this, okay. But then what we do, we use a throttle like this. So, basically there is a blockage here, and because of this blockage you will have basically the nature of the flow is that it will try to push this on the upstream side, and that may lead to unstart. So, if you want to solve this problem, you will have to basically make a very complicated grid. Okay. So, there are multiple blocks here, you can see there are, this is a multi block structured grid. So, maybe 1 2 3 4 5 6 7 8 9. Okay. They are the blocks that you have to make. You have to make a very nice structured grid. I mean, you can do unstructured also, but structured is better in terms of accuracy. And we have done with like there is no throttle. Okay. So, which is basically there is a straight line here. Okay. There is no unstart and there is a high throttle here. The throttle ratio is 0.42 and throttle ratio is 0. Okay. And because of this flap, you can change the angle of the flap, and accordingly you will have the push on the upstream side. Right. So, the experiments were done in ISC. I think there should be some reference in our paper. Okay. I do not know if I mentioned there. Yeah. So, this is one of the papers that we have with my student. Okay. So, this is the Reynolds number is around a million. Okay. Mach number is 6. Okay. In fact, around 9 million. Okay. Pressure and temperature are given. Okay. Again, once again we use the open form, rho central form, U rans, because these flows are unsteady, so you cannot use steady rans. Yeah, these are density based solvers, we have already discussed explicit formulation, time stepping, and these are the gradient, divergence, Laplace schemes. Okay. And the maximum CFL number we have played with different values and found it to be stable at these values. Yeah, but it also depends on how good your grid is. Okay. Viscosity is Sutherland's law, and turbulence you have Mentor's SSTQ omega model. Okay. The default model, and you can see that when there is no flap, okay, then it is nicely you can see all the structures, the separation region being formed here, the shock bond induction and all those things are basically captured here. There is a separation formed here also. So, all these things are shown there. Okay. Once we have basically a throttle, and the throttle goes to a significantly high value, you will have basically structures which are getting developed here. Okay. And at I think TR 0.4 or something like that, okay, they will start traveling upstream. Okay. And then they lead to phenomena called little buzz or big buzz. Basically, these are the unstart phenomena which are basically dangerous for the operation of these scramjets. Okay. So, yeah, these are the things that I just wanted to show, that if you are interested in research, okay, you have to solve some complicated phenomena. You can do simulation, let us say in a nozzle also. Okay. And we have some studies like that as well. But the idea is to give you a flavor at the end of this course, is that you have the understanding of the theory of gas dynamics. You know how to solve using I mean the problems of gas dynamics computationally. So, if you want to solve very challenging problems computationally, then you should have basically good understanding of both the theory as well as the numerics. Okay. You should have command in both, and sometimes it is a frustrating experience because your solver setup does not work, or it does not give you correct result, or it blows up. But ultimately, if you look dive deep, and once it works, you would know that what mistake you are doing. Okay. And that will only that understanding will only come once you understand that okay, these are the schemes, they will work in these conditions. Okay. And these are the limiters, for example, every setup that you have, everything that you have in your solver need to be perfectly fall in place to get simulations right for a complicated problem. For simple problems, I mean you use rho scheme, AUSM, rho central form, sonic form, they will all give decent results. Okay. As soon as the problem becomes complicated, okay, then you have to be really careful about how to set up a solver. Okay. So, I hope this course was useful to you, and you had some understanding of how to solve problems in gas dynamics, and I suggest that you start solving some simple problems. You start with simple problems, okay, and use any solver that you like. Okay. Just understand what you are doing, do not use it blindly. Okay. Do not use it like a black box. Okay. So, and then you will develop understanding of computational gas dynamics, and then you can basically further take it to solving more complicated problems. Okay. With that, thank you very much, and you stayed with us for this all these 12 weeks. I hope that you gained something. Thank you once again.